Now, these are some important calculations that could be involved here and there, right? In your overall scheme of things in rotational mechanics, calculations related to moments of inertia would be very vital, very critical. Now, some basic notions, because we're going to embark on the mission rigid body dynamics. It's important to understand what a rigid body is. Very important to understand what a rigid body is. Essentially, this is a rigid body. And if A and B were any two particles of the rigid body, if you monitor A and B, any two particles constituting the rigid body, if you monitor A and B, the rigid body could be in a state of very complicated motion. But if you monitor the motion of A and B over a period of time, then one thing that could not change with time is the separation between A and B. The separation between A and B will not change with time. The relative separation between A and B, any two particles, any pair of particles A and B remains unaltered. That's the physical understanding of a rigid body. Now, in a very complicated motion of the rigid body, any given instant of time, A and B could have different velocities. In general, A and B could have different velocities in general. Say if I find at a given instant the velocity of A in VA, making an angle alpha with the line joining the two, and VB, the velocity of B is VB, magnitude VB, making an angle beta with AB. Now, their velocities could be resolved along AB as VA cos alpha and VB cos beta. Along the line joining A and B, their velocities could be resolved as VA cos alpha and VB. And perpendicular to the line joining them, their velocity components would be VA sin alpha and VB sin beta. Yes or no? Yes or no? Resolving their velocities along AB and perpendicular to AB. This is what you get. Now, their relative velocity along AB is what? VA cos alpha minus VB cos beta? Yes or no? Right? Relative velocity along AB, their relative velocity along the line joining A and B, along the join of the two particles, is VA cos alpha minus VB cos beta. Hey, if it's a rigid body, and if this velocity is not zero, then the distance between A and B would change with time. The relative velocity along the line joining the two is not zero, then the separation between A and B would change with time. And therefore, a necessary requirement for it to be a rigid body is that the relative velocity along the line joining the two must necessarily be zero. The relative velocity along the line joining the two must necessarily be zero. Means their velocity components along the line of their join must be the same. Their velocities along the line AB must be the same. Their velocity components along AB ought to be the same, so that their relative velocities along AB is zero. So this is the kinematic requirement for a rigid body. This is a kinematic requirement for a rigid body, right? And this is true for any pair of particles constituting the rigid body. Got me? Now, very complicated kind of a motion executed by a rigid body. Very complicated kind of a motion executed by a rigid body. Different particles of the rigid body would have different velocities as long as they subscribe to the basic rigid body requirements. That is, the relative velocities along the line joining the two must be same, right? But then in general, different particles have different velocities. So, for a rigid body, in a very complicated kind of a motion, will give you a particle that has zero velocity. You can identify a particle in a very general rigid body motion having zero velocity, which means, see, there is a particle A that has velocity V, There is a particle A that has velocity V. And there is a particle P whose velocity is zero. There is a particle P whose velocity is zero. And A is any other particle that has a velocity V as shown. This particle that has zero velocity is called the instantaneous center. This particle P that has zero velocity is called instantaneous. It's called instantaneous center. It's called the instantaneous center. This particle P that has zero velocity is called the instantaneous center. Now, if you join A and P, and say this angle is alpha, angle that this velocity makes with AP. What's AP? AP is the line joining the particle A to the instantaneous center. AP is the line joining the particle A to the instantaneous center. Now, if it's a rigid body, their relative velocity along AP must be zero. That means velocity of A along AP must be equal to velocity of P along AP. What's velocity of A along AP? V cos alpha. And that must be velocity of P along AP, which is zero. Means if V is not zero, alpha must be 90 degrees. Cos alpha is zero, so alpha must be 90 degrees, which means V must be perpendicular to AP. V must be perpendicular to AP. Are you alright? Are you alright with this or not? Right? If there is some other particle B, you join B and P. Now, once you have identified point P with zero velocity, and you're going to call it the instantaneous center. And this is the instantaneous center at this instant. At some other instant, you might have some other instantaneous center. That's another issue. You're looking at another particle B. So the particle B will have velocity that will also be perpendicular to BP. The particle C will have a velocity V double prime, which will also be perpendicular to CP, and so on and so forth. Yes or no? You will have a particle D whose velocity V triple prime would be perpendicular to PD, and so on and so forth. Are you alright with this? And therefore, that at this instant of time, this is the instantaneous center, call it IC, whose velocity is found to be zero. How to locate the instantaneous center? Another issue. Let's say this point B, the instantaneous center, this point A, At this instant of time, the velocity of A is perpendicular to AP. The velocity of A is perpendicular to AP at this instant of time, right? Means, from the perspective of P, the instantaneous center, from the perspective of P, the instantaneous center, I can imagine A to be moving in a circle of radius R with a tangential velocity V, yes or no? I can imagine A to be moving in a circle of radius R with P being the center of that circle, with P being the center of that circle with the tangential velocity V, with the tangential velocity V, yes or no? Right? And with omega equal to V by R, and with omega equal to V by R, are you alright with this? Right? So, all particles could be, the particle B would be moving in a circle centered at P at this instant of time with radius equal to BP and tangential velocity equal to V prime and so on. So, it's as if all the particles at this instant of time could be kinematically imagined to be moving in circles of various radii in general with a different tangential velocity. Now, and what is the instantaneous center? It's the point identified to be having zero velocity. That's the instantaneous center. Got me? Now, in a rigid body, again with very general kind of motion, if someone gave you the velocities of two particles, particle A1 and let's say particle A2. Particle A1 and particle A2, their velocities were known. For a rigid body, they gave you, or let's say you could find the velocities of two particles, A1 and A2, the directions, even if it's not the magnitude, but you had the directions available. And if you are asked to find the instantaneous center of this rigid body, then, well, the instantaneous center must lie on a perpendicular to V1 passing through A1, and the instantaneous center must also lie on the perpendicular to V2 passing through A2, and the intersection of the two will give me the instantaneous center. Draw perpendicular directions to any two velocities, the intersection of that will give you the instantaneous center. The point, imagine to be having zero. This point has zero velocity, but not zero acceleration. That you must remember. The instantaneous center has zero velocity, but not zero acceleration in general. Right? So far, so good. No problems with this, right? All of you understand everything that I've said so far, isn't it? So this is an important consideration, identifying a point within the. Now, this point P, by the way, this point P may actually lie outside the rigid body. It may not necessarily lie inside the rigid body, right? Which means, for example, say, this is a ladder AB. This is the wall and this is the floor. And that's the wall, right? And the ladder slides, right? When the ladder slides, you realize this is a rigid body. AB is a rigid body. This is the ladder. A is bound to have a velocity VA along this only. There's no other way. The velocity of A has to be like this only. And the velocity of B has to be like this only. And now you have to locate the instantaneous center. If you have to locate the instantaneous center for this rigid body, then well, draw a perpendicular to VA, draw a perpendicular to VB, and the intersection of the two will give me the instantaneous center of the rigid body, the point P, the instantaneous center of the rigid body. Got me? So in this case, it lies outside the ladder, as you can see, it lies outside. Right? Are you confused? So it may lie within the precincts of the body, or it may lie outside the rigid body. The instantaneous center conceived to be having zero velocity, and all of the particles of the rigid body, from the perspective of the instantaneous center, to be moving in circles of various radii centered at the instantaneous center. Got it? So with a rigid body in general motion, one important point is the instantaneous center, point that has zero velocity, not necessarily zero acceleration, right? Now, this is a recap of things that I might have said before, but I quickly reiterate these things. The three kinds of motion that you're going to encounter in general. One is pure translation for a rigid body. Pure translation means, let's say this is a rigid body in a state of pure translation. This is the center of mass, and VCM is the velocity of the center of mass. Then the velocity of any other particle, let's say the ith particle constituting the rigid body, will be the same as the velocity of all particles constituting the rigid body in a state of pure translation will be the same as the velocity of the clear? That's pure translation. All particles have the same velocity in pure translation, right? And then you have pure rotation. Pure rotation. See, this is a rigid body, and it's hinged about P. It's hinged about P. It's hinged about P. Hinged about P. Then this would be the axis of rotation. This would be the axis of rotation. That means after a while, the rigid body in general like this. Let's say this angle theta would change with time, this angle theta would change with time, and rate of change of this angle theta would measure what we call the angular velocity of the rigid body. The rate of change of this angle theta is called the angular velocity of the rigid body. It's called the angular velocity of the rigid body. In a situation of this kind, all particles will move in circles centered at this point P, which is the hinge. All particles will move in a circle centered at P, and realize that the rate at which theta changes with time, omega, the angular velocity, would be the same for all particles constituting this. In pure rotation, omega will be the same for all particles. Say if this is a particle A, and after a while it moves to A prime, and in the process A describes an angle theta at the hinge, then any other particle B will also describe the same angle theta. So if you look at a particle B, B moves to B prime, then B also describes the same angle theta at the hinge. Yes or no? So all particles are describing in a given time the same angle theta at the hinge, the same angular velocity of. So in pure rotation, all particles will have the same omega about the hinge, right? So omega is the same for all particles about the hinge or about the axis of rotation. This is the axis of rotation. This is the axis of rotation. And also means that in pure rotation, say omega is the same for all particles constituting the rigid body. This is the hinge P, this is the hinge P. This is a certain particle A, and its distance from the hinge will not change with time. So it's going to execute circular motion with angular velocity omega. This particle A will execute circular motion with angular velocity omega centered at P and of radius. So then it will have a tangential velocity VA, which would be RA omega, which would be RA omega in general. Omega is the same for all, but RA is different for different A's. So in general, the velocities of different particles will be different. The tangential velocity or the linear velocities will be different for different particles, but omega will be the same. Pure rotation, all particles have the same omega, all particles have the same omega, but in general, they have different particles have different linear velocities. These velocities are also tangential velocities. They will be perpendicular to the radius. Right? So VA is different for different A's, but omega is the same for all A's in pure rotation, in a state of pure rotation. Now, it's also important to understand. See, so far, we've spoken of. So far, you have spoken of omega of particles, right? But what about omega of rigid body? What about omega of rigid body? You know, one should not get restrictive in understanding what omega of rigid body actually means. What the omega of rigid body? You please have this settled in your head once and for all, simple idea, and never to mess it up with omega of particles, right? See, if this is a rigid body, this is a rigid body, and you choose any 2 points on the rigid body, say A and B. Any 2 points on the rigid body, say A and the rigid body undergoes a very complicated kind of motion, say different particles in general having different velocity. Different particles in general having different velocity. Now, if someone speaks of the omega of the rigid body, then what's going to measure the angular velocity of the rigid body? Now, I'm not talking of the omega of a particle. I'm talking of omega of a rigid body. So, rigid body, what does that actually mean? This is at certain time t equal to 0. You take a sketch pen and mark this line AB. Mark this line AB at time t equal to 0 on the rigid body, joining A and B. After a while, you find that AB gets reoriented. After a while, you find that AB gets reoriented. Say the position of AB now becomes this A prime, B prime. At a certain time t, at a certain instant of time t, the orientation of AB will now become, say, A prime, B prime. What then will measure the omega of the rigid body? Well, what you do is take this AB, superimpose it right here, move it parallel to itself, bring it here. This was the original AB, and this was the original orientation, and this is the revised orientation. Then this angle that it has got, this is the angle by which it has got reoriented, will be a measure of omega. If theta was more, the omega of the rigid body was more. The omega of the rigid body is about how any one line chosen on the rigid body reorients itself with respect to time. How fast this line AB reorients. What's the reorientation factor? Theta. How fast theta changes with time. How fast theta changes with time will be a measure of omega of the rigid body, right? And by the way, whether you choose this line as AB or you take any other particle, A prime, B prime, and you measure the extent to which they have got reoriented, it will be the same for a rigid body. The extent to which AB has got reoriented in a given time must be the same as the extent to which A prime, B prime would have got reoriented in a given time, right? So then, it does not matter the selection of the particles for the sake of calculating the omega of the rigid body, right? So we are not talking of omega of a particle about a point. We are talking now in a very universal sense, omega of a rigid body. Omega of a rigid body, which is like how any line on the rigid body is getting reoriented with time. And that's going to be a measure of the omega of the rigid body. So this rate of change of this theta with time will be a measure of omega of the rigid body, and it's independent of the selection of the line on the rigid body for the sake of this calculation. Got it? So omega of the rigid body would be rate at which this theta changes with time, how a given line, how fast a given line reorients with time, and this omega in general could be different for different theta. This omega itself could vary in general for a rigid body, right? If this omega itself is varying for a rigid body, we say that the rigid body is in a state of angular acceleration. This is the angular velocity of the rigid body. This is the angular velocity of the rigid body. And if this also changes with time, we say it's in a state of angular acceleration. The angular acceleration of the rigid body is how fast omega is changing with time. How fast omega is changing with time is the angular acceleration of the rigid body. Got me? Right? So far so good, right? Now, let me also tell you, this is important. I hope you're not confused, because see, these are, although I'm just trying to give you a very basic idea, but these are important ideas. So, any lacuna left here will get compounded, super compounded, and will leave you helpless if you've not understood it right now. So, I just want you to understand my perspective of things here, because I'm going to echo and voice the same things in different formats. So, are you all fine with everything that I've communicated so far, right? Now, also telling you that if P is the instantaneous center of the rigid body, if P is the instantaneous center of this rigid body, right? One way of calculating omega is going this way, right? You take any line and rate at which this theta changes with time. The other way of calculating omega for the rigid body is the following. You identify the instantaneous center, P. You identify the instantaneous center, P. Like I told you, how could you identify the instantaneous center? If you have knowledge of the velocities of any two particles, then draw perpendiculars to those two velocities. The point where the two perpendiculars intersect would be the instantaneous center. Now, once you locate the instantaneous center of the rigid body, then the omega of the rigid body can be calculated from the instantaneous center ideology. How? Look, this is the line joining the particle A to the instantaneous center. So the velocity of A has to be perpendicular to this, right? So at this point of time, you can imagine A to be moving in a circle of radius R centered at P. So then the omega, the rate at which A is reorienting itself with time, the omega for A, which is like V by R, referred to the instantaneous center, right? V of A is R times omega of A, so omega of A is V by R. This omega A is the same as the omega of the rigid body. This omega A is the same as the omega of the rigid body. You know what I'm saying? So, from the knowledge of kinematics of one of the particles, the omega of the rigid body could be obtained. Right? If you've located the instantaneous center. Which means refer to the instantaneous center. Refer to the instantaneous center. All the particles, say, of the rigid body are in a state of pure rotation, with angular velocity omega. Please write down. Refer to the instantaneous center. Refer to the instantaneous center. All the particles constituting the rigid body, could be imagined to be in a state of pure rotation. In a state of pure rotation, centered at the instantaneous center, and with angular velocity, same as that of the rigid body, Right, also write down the instantaneous center. Thus, reduces a very complicated motion, into a state of pure rotation about itself. Got me? So that's the idea behind the omega of a rigid body, right? And then this omega will coincide with the omega that you compute for a given particle, imagining it to be in a state of pure rotation about the instantaneous center. No issues with this, right? Are you all fine with this? So then, I told you what pure translation is. Pure translation means all particles have the same velocity as that of the center of mass. I told you what pure rotation is. Now all particles have the same omega about the hinge or the axis of rotation, right? And I told you what I mean by omega of a rigid body in general, right? And how that omega could be computed in different ways, by examining how a given line reorients itself in space, or by looking at the instantaneous center and calculating the omega for a point particle moving in a circle of radius r with velocity v centered at the instantaneous center, right? Now, the most general motion, which is our objective, is a combination of pure translation and pure rotation. In pure translation, it was enough to know what the velocity of the center of mass was, right? The center of mass was moving. In the state of pure rotation, it was enough to know what omega was, because with the knowledge of omega, v equal to r omega could be obtained. So all particles have the same omega, so omega characterized pure rotation in and out comprehensively. Combination then of pure rotation and pure translation is what we call as the combined motion or the general rigid body motion. Or general rigid body motion. Combined motion or general rigid body motion, where this is a rigid body This is its center of mass. The center of mass speaks of the translation of the rigid body. Speaks of the translation, the physical movement of the particles of the rigid body, VCM. VCM, therefore, velocity of the center of mass, therefore, characterizes translation in a rigid body. Characterizes translation in a rigid body. Right? And then, any given line on the rigid body will reorient itself with time. If you choose any given line on a rigid body, then in a very general motion, it will reorient itself. If it was pure translation, in a pure translation, if you select A and B, then A moves by a certain distance, B moves by the same distance in a given time, and then A prime, B prime will be parallel to AB, and there will be no reorientation of AB in pure translation. You realize that? In pure translation, a given line AB on the rigid body will remain parallel to itself. Are you fine with this or not? Right? But in pure rotation, in a motion where there is angular velocity of the rigid body, this AB, if there is omega, then this AB would reorient itself with time. Not only will it move physically to the right, commensurate with VCM, it will also tilt. It will also tilt in a period of time. So then this omega will measure how rapidly AB is tilting with time. How any line AB is tilting with time will be measured by the angular velocity of the rigid body, right? So this is general rigid body motion, in which two things are simultaneously present. One is velocity of the center of mass. One is velocity of the center of mass, which only causes physical movement parallel to itself of any line, right? And then there is omega, which will cause AB to tilt. And it will keep tilting. At the rate at which it tilts will be a measure of omega of the rigid body, right? Now, this general rigid body motion, in which there is translation as well as rotation, could be looked on as a superimposition of pure translation and pure rotation. It means this motion could be looked upon as superimposition of, let's say, pure translation, where every single particle has the same VCM. Every single particle has the same velocity, synonymous with the center of mass, plus. Imagine it to be in a state of pure rotation about the center of mass. Pure translation plus pure rotation about the center of mass with angular velocity omega will be this motion, which is general rigid body motion, in which two things will characterize the motion completely: a VCM and omega, a VCM and omega, right? VCM will measure the translation, and omega, imagine the rigid body to be in a state of pure rotation about the center of mass. The combination of these two will tell you the combined motion, will tell you everything about the combined motion, right? Imagine it to be in a state of pure translation with a velocity equal to velocity of center of mass, plus imagine it to be in a state of pure rotation hinged at the center of mass, with an angular velocity omega. You know what I'm saying? Means now this is general rigid body motion, completely uniquely characterized by a VCM and omega. This is general motion, right? In which there is reorientation as well as translation. Reorientation because of omega and translation because of VCM, right? Like I said, it's the superimposition of pure translation and pure rotation about the center of mass with an angular velocity omega. plus pure rotation about the center of mass with angular velocity omega. Hello? What good is it? Look, this is the center of mass. This is the center of mass. This is a certain particle P located at a distance r, from the center of mass. And I want to be able to find the velocity of this point. Given general motion of this kind, Vcm and omega given, I want to find the velocity of a certain point P on the region. What I do is, P was here. Alright. Because of pure translation, this P had a velocity Vcm like this. Had a velocity Vcm like this. Let me call the center of mass SO. Center of mass SO. Now, this P, once again, look at P. Because of pure rotation, you can imagine P to be in a state of pure rotation about O with a velocity Vp, V tangential equals r omega. Because it's in a state of pure rotation about O, it has a velocity perpendicular to the radius. Equal to r omega because of pure rotation. The net velocity of the point P would be the vector sum of this Vcm and this r omega. This Vcm and this r omega, the vector sum of these two will give me the net velocity of the point. So this point P has a velocity which is like a Vcm like this. Because of pure translation and because of pure rotation, it has a velocity perpendicular to r, which is r omega. Now, the vector sum of these two velocities, which can either be obtained by resolution or by parallelogram law, this will give me the net velocity of the point. This will give me the net velocity of the point. Right? So, given Vcm and omega, using this superimposition of pure translation and pure rotation, you can obtain the velocity of any point. So, the entire velocity field is at your disposal. Given Vcm and omega, the entire velocity field is available to you. Are you alright with this? So, Vcm and omega are pretty complete in representation, right? Together, they give you a ground to calculate the velocity of any particle of the rigid body, right? And therefore, so actual motion is complicated. It's a combination of pure translation and pure rotation, both, right? Now, the rigid body given by a Vcm and an omega. Given by a Vcm and an omega, right? Now, think of a point P here, right? At a distance r from the center of mass O. And if I want to find the velocity of this point P, it's going to be Vcm because of pure translation, right? Next, imagine it to be in a state of pure rotation about the center of mass. with angular velocity as shown. Then it will have a velocity perpendicular to r like this, right? Tangential velocity perpendicular to r like this, which is r omega leftwards because of pure translation, right? You can find, so the net velocity of point P is like the superimposition of this Vcm and this r omega, which are now in opposite direction, right? You can therefore model a r, select a r such that VCM becomes equal to R omega. You can select a point P whose R is such that VCM becomes equal to R omega. If VCM becomes equal to R omega, then the net velocity of the point P becomes 0 for this R. For this R, the velocity of the point P becomes 0, right? And if this point P becomes 0, then P is instantaneous center. P is the instantaneous center. P then becomes the instantaneous center. If this happens, then P is the instantaneous center. Now it's a one-time effort to find the instantaneous center at a certain instant of time. And once you have located the instantaneous center, the world is at your disposal, because, say, take the instantaneous center P, a point with 0 velocity, then for sure, you don't, the entire motion which was superimposition of pure translation and pure rotation. Now about the instantaneous center, it's in a state of pure rotation about P with an velocity equal to omega. Locate the point P, and if you have knowledge of omega, if you have located the instantaneous center with the help of this and you have knowledge of omega, right? I hope I am conveying things to you in a manner that you can understand, right? Then look at this point Q, whose velocity otherwise we would have obtained by a combination of pure translation and pure rotation. But now the velocity of Q, given the instantaneous center, can be obtained without getting into the messy affair of superimpositions. You, first of all, finding because of pure translation, pure rotation, and then using the parallelogram law, which you took such a long time to learn. By this time, you would have forgotten that also, right? So then what you do is, well, this is the instantaneous center. Velocity of Q has to be perpendicular to this R naught. So the velocity of Q is R naught omega, which can be obtained without any superimposition now, because you can imagine the entire body to be in a state of pure rotation about the center V. Once you obtain the instantaneous center and you know omega, then the velocity of any point can be obtained without any complications, right? So that's the merit of invoking a concept like instantaneous center, right? It's only a figment of our imagination. P may or may not be a point on the rigid body, yet extending the rigid body to include P would be an idea that warrants a lot of merit. It gives us a lot of versatility in operations, right? Can I back this off? Now, in a rigid body, like I said, omega is measured by the reorientation produced on a given line, the rate at which reorientation occurs on any given line which is x out in the rigid body, right? Say, this was a rigid body. This was a line joining a pair of particles A and B. This was a line joining a pair of particles A and B. And say the velocity of A was VA, making an angle alpha, and the velocity of B was VB, making an angle, and the separation between A and B was L. These are any two arbitrary particles on the rigid body. And we've identified a pair of particles whose velocities are as shown. Right? L is the separation between A and B, which is not going to change with time. Right? Now their velocities, like before, could be resolved as VA sine alpha this way, VA cos alpha this way, VB sine beta this way, VB cos beta. Yes or no? How? VA cos alpha is VB cos. VA cos alpha is VB cos beta. That's a rigid body requirement. Velocity along the line joining the two is 0. Right? So now somebody says, what's the velocity of A as seen by B? Their relative velocity in this direction is 0. So their net relative velocity has to be in this direction only. Their net relative velocity has to be in this direction only. That means, what would B report about A? Right. B, that means imagine B to be at rest. Imagine B to be at rest, an observer. Imagine B to be an observer. Then B will report about a velocity in this direction, which is not VA sin alpha. It will report VA sin alpha minus VB sin beta. Right. VA sin alpha minus VB sin beta. Because in this direction, the velocity of A as seen by B is 0. So the net velocity of A as seen by B would be VA sin alpha minus VB sin beta. Are you alright with this or not? That's the velocity at this instant of time seen by B of A. Right? Which means at this instant of time, B will suggest that A is moving in a circle of radius L and with a velocity, tangential velocity VA sin alpha minus VB sin beta. See the omega, therefore the omega of the rigid body, will be the omega of A as seen by B. Omega of A as seen by B will be the manner in which AB is reorienting with time. Will be the manner in which AB is reorienting with time. So that's going to be VA sin alpha minus VB sin beta by L will be the omega of A. And if VA sin alpha minus VB sin beta is positive, then this velocity is like this. That means omega is clockwise. If this is negative, then the velocity of A as seen by B is downwards. Then the omega would be anti-clockwise. The omega of the rigid body is going to be anti-clockwise. Are you fine with this or not? Right? Raghav, got me, na? So that's another way you can compute the omega for a rigid body. If you have knowledge of the kinematic status of two particles A and B, VA and VB with alpha and beta known to you, the omega of the rigid body could be obtained at that instant of time using these considerations. Right? All right. Now, once you understand this basic relevance of the rigid body dynamics in terms of particles and their kinematic status, it's important for me to tell you a few more related. One, the angular momentum ideas. I'll go very basic, very simple. All right. I'm not going to right away take you through complicated things. Right? Very simple, because you understand the simple stuff and you're right there. All right. I'll dispense away some of the things which will only add burden to you right now and will not improve understanding. So I'll kind of shed away those things and I'll go for first one. One is if there is a particle P, whose magnitude of velocity is V, whose magnitude of velocity is V, right? And there is a point O, and there is a point O. This is the line of action of the velocity. This is the line of action of the. And if the mass of this particle is m, if the mass of this particle is m, then this is O. The linear momentum of this particle, small p, is going to be m into v like this. Along the velocity, its linear momentum is going to be m into v like this, right? M into v, right? Now, this is the line of action of the linear momentum. Just to make it more pronounced, this is the line of action of the linear momentum. This is the line of action of the linear momentum of this particle. Now, the perpendicular distance between the line of action of the linear momentum and O, if that's R, the line of action is at, bless you, is at a distance R from the point O. This is the line of action of linear momentum. If that's at a distance R from O, then we define the angular momentum about O. Magnitude, angular momentum about O. Linear momentum is m into v. The angular momentum, magnitude of the angular momentum about O is defined then as mv into the perpendicular distance r. Mv into the perpendicular distance r. That's angular momentum about O. Angular momentum is a vector whose magnitude about O for the particle P shown is mv into r, right? The direction of the angular momentum. Although the direction will be like as per the requirements of vectors, but more than the direction, we'll talk of the sense of the angular momentum. We'll talk of the sense of the angular momentum. More than the direction, we'll talk of the sense of the angular momentum. That's more relevant. The angular momentum, in order to find the sense of the angular momentum, you imagine the following, mentally imagine the following. This was O, this was M, and this was the line of action of the linear momentum. This was the line of action of the linear momentum. This was R. This was the line of action of the linear momentum, and this was. Now, the magnitude of the angular momentum about O, this is angular momentum about O, is mv into r. Now, the sense of the angular momentum, I won't talk of the direction right now. The sense of the angular momentum, what we do is, instead of this being the linear momentum, think of this as a force and think of this as a rod. Think of this as a force acting at this end of a rod, which is hinged at O, Think of this as a force, mentally imagine this to be a force and this to be a rod hinged at O. When you apply a force like this rod about O would rotate clockwise, yes or no? If you apply a force in the direction of the linear momentum on this rod hinged at O, then this rod would rotate clockwise, yes or no? Right? The sense of rotation of this rod that we are only mentally imagining, the sense of rotation of this rod, perpendicular rod that we are mentally imagining, is the sense of the angular momentum. In this case, the sense of rotation of the rod is clockwise. So, the sense of the angular momentum here is clockwise. So, this L we say is clockwise angular momentum about O. Clockwise angular momentum about O. Yes or no? Right? In contrast, This was the particle, and its linear momentum P was magnitude m into v, like this. Clear? And the point O was located here, and the point O was located here. Instead of being below this, it was this was the line of action of the linear momentum. This is R. When it was forces, we called it the momentum. Now we are going to call it angular momentum arm. We'll call it the angular momentum arm. Earlier case, we called it the moment of the force. Now we'll call it the angular momentum arm. We'll call it the angular momentum arm. Right? So this was mv, and the line of action of mv was at a distance r from the proposed point O. Now, the magnitude of the angular momentum, once again, will be mv into r. That will be the magnitude of the angular momentum. Magnitude of the linear momentum into the perpendicular distance of the line of action of linear momentum from the point O. That's the magnitude of the angular momentum. What about the angular momentum? Because what you do is, imagine, just mentally imagine a force to be acting like this. Imagine a rod to be fixed at O. Then this rod will move in this sense. This rod will rotate in this sense about O, which is anti-clockwise. So in this case, the L about O is anti-clockwise. L about O is now. So for a given particle, clockwise angular momentum, anti-clockwise angular momentum, and how to calculate the magnitude of the angular momentum, you understand. Now we go from one particle to a collection of particles. Now this collection of particles could be in a state of pure translation, could be in a state of pure rotation, or could be in combined general rigid body motion. How do I compute the angular momentum for a collection of particles? Right? For a collection of particles, the basic idea is simple. The angular momentum would be the algebraic sum of the angular momenta of the constituent. This is all that you need to do, right? But then let's model it for pure translation, pure rotation, and general rigid body motion, right? Again, in a very simplistic manner. I hope you're not confused about anything that I have said so far on angular momentum, right? Say, pure translation. All particles have the same velocity, VCM. All particles have the same velocity, VCM, right? And the center of mass in pure translation is the representative particle. Means I can replace this entire collection by a point mass located at the center of mass. So this is the same as one single particle of mass m having a velocity VCM, Now, I want to calculate the angular momentum about O. For this collection of particles in the state of pure translation. Well, what I do is say this distances. So what I'm eligible to do is replace this entire collection by a point mass placed at the center of mass, and the point O is located here at a distance r. So what's going to be the angular momentum here? Total mass of the collection into VCM into r. Is it clockwise or anti-clockwise about O? Clockwise. Imagine a force to be acting along VCM. Imagine this to be a rod hinged at O. This rod will rotate. So in this case, this L about O is clockwise. Clockwise. This L about O is clockwise. For this pure rotation, in pure rotation, right? Now, pure rotation. Pure translation simple. Replace the entire collection by a point particle at the center of mass and then MVCM into the perpendicular distance. Angular momentum arm is R. Angular momentum arm is pure rotation. In pure rotation, you will find a hinge. All particles have the same omega, right? This is pure rotation about a hinge H, about a hinge H. Right? And all particles in pure rotation will have the same angular velocity about the hinge. This will be the axis of rotation. This will be the axis of rotation. Omega is right. I then think of a particle of mass mi. I then think of a particle of mass mi at a distance ri. Think of a particle mass mi at a distance ri. Clear? Now, I want to compute angular momentum about H, about the hinge. I want to compute angular momentum about H. One thing, particle is in a state of pure rotation about the hinge with a velocity Vi equals Ri omega, where Ri is the distance from the axis of rotation, right? So then, Mi into Vi is the linear momentum, into the angular momentum arm, which is Ri. That's the angular momentum contributed by this particle about the hinge edge, right? The total angular momentum about the hinge edge would be the sum of all of this. The total angular momentum about the hinge edge would be sum of all of this, yes or no? Where, what is Vi? Vi is Ri omega. Writing Vi as Ri omega, so Mi Ri squared into omega. Hey, but omega is the same for all I, so omega will regularize here. Omega comes out, and then we have summation Mi Ri squared. Hey, but Mi Ri squared is what? I about H. Is the moment of inertia about H? Mi Ri squared is moment of inertia about H, right? So then this is I about the hinge into, right? So in pure rotation, the angular momentum about the hinge, which is most important. In pure rotation, the angular momentum about the hinge would be I about the hinge into omega. If omega is clockwise, L will be clockwise. If omega is anti-clockwise, L would be right. Now, in combined motion, I'm not, see, it requires derivation, but I'm not going to derive that right now because I want to scrape through almost everything in rotation, superficially at least. So I'm not going to derive the next result for you, but at the same time, I want you to know this result, right? That is the angular momentum in combined motion, right? angular momentum and combined motion. Combined motion means I have a rigid body characterized by VCM and an omega. This is the point O, which is the center of mass, and I want to find the angular momentum about, let me call it C1, about O. I want to find the angular momentum about O for this collection of particles in a state of general rigid body motion. Not only are they translating, a line is also reorienting itself because of, right? Say this distance is small r, OM is small r. I want to find the angular momentum of this system about O. Like I said, it could be reduced to pure translation and pure rotation. Pure translation pure rotation about the center of mass, right? That means imagine the center of mass to be the hinge. Pure rotation. Now, the angular momentum about O without deriving things for you, About O, if you have to compute the angular momentum for a general rigid body motion, it would have two terms in it. One, that would depend on where O is located. Two, there would be a term that will not depend on where O is. Mentally, the manner in which I want you to remember this, think of the pure translation, which is like a point particle placed at the center of mass, M, VCM into R. That's the contribution because of pure translation. The contribution because of pure translation is MVCM into R, clockwise or anti-clockwise? Clockwise. Why? Because imagine this to be a rod. Imagine a force to be acting in this direction. The rod would rotate. Right. So because of pure translation, the L about O because of pure translation is going to be M VCM into. Add to it I angular momentum about the center of mass. Angular momentum in pure rotation about the hinge is what? I about the hinge into omega. So I about the center of mass in pure rotation is going to be I Cm into omega. That's for pure rotation, right? That's the result for pure rotation, yes or no? Right? In pure rotation, the angular momentum about the hinge, in this case, the center of mass is the hinge. So ICM into omega. Now, this, by the way, is clockwise. This is clockwise. MVCM into R is clockwise. And this omega is also clockwise. So this is also clockwise. This is also clockwise. Confusion. No? So the net angular momentum about O, in this case, the net angular momentum about O would be the algebraic sum of these two. So it's going to be mvcm into r plus ICM omega. mvcm into r plus ICM omega. Both are clockwise. So the sum would be clockwise. So the sum would be clear. So that's when I said if you want to find the angular momentum of auto in general rigid body motion, it will have two terms in it. One, that will depend on where O is located. This will not depend on where O is located. Got me? If you have to find the angular momentum about the center of mass alone, then this R will be 0. It will simply be ICM omega. Even in general rigid body motion, this is general rigid body, this is L about any point O. But if you want to find L about CM, then put this small r equal to 0. So then this will be mvcm into, ICM into omega. It's simply going to be ICM into omega. That's angular momentum about the center of mass in general rigid body motion. This is L about the center of mass in general rigid body motion. This is L about any point O in general rigid body motion. Has two terms. One, that will depend on where O is located. Two, second term will not depend on where O is. If I had say something like this, general rigid body motion with this being BCM and this being omega, and the point O was located here. This was R, right? Then do you realize that if I have to now compute L about O, I'll have one term that does not depend on O, that's going to be ICM omega, that's going to be clockwise. ICM omega, that's clockwise, which will not depend on where O is, right? Now, there is mvcm into R is anti-clockwise. Do you realize that? This, imagine this to be a force, this to be a rod, then this rod would rotate anti-clockwise. So then there would be a component mvcm into R which is anti-clockwise. So the net angular momentum of auto is going to be the algebraic sum of clockwise and anti-clockwise. So if you call all clockwise angular momentum positive, then all clockwise angular momentum would be referred to as net angular momentum of auto is going to be, let's say I choose clockwise positive, anti-clockwise negative. So ICM omega minus mvcm, that's the net clockwise angular momentum. That's the net clockwise angular momentum. If this is right, if this number turns out to be positive, then it's positive. This turns out to be negative, means the angular momentum is anti-clockwise. That's what it is. Clear? Like I said again, in pure rotation, if you hinge a particle at a point P, if you hinge a particle at a certain point, then the angular momentum about the hinge is going to be I about the hinge into omega in pure rotation, Do you realize that combined motion, the most complicated motion, could be reduced to pure rotation if you look at the motion in light of the instantaneous center? Yes or no? Right? The omega, however, whether you obtain it from the instantaneous center or you from Thailand, it's going to be the same, right? So, even if it is general rigid body motion, you can identify the point P, which is the instantaneous center, right? And then all particles will be in a state of pure rotation about the instantaneous center. From the instantaneous center, there is no general motion. It's only pure rotation. From the instantaneous center perspective, it's only pure rotation. with omega now being the same as the omega obtained earlier in general rigid body motion, right? So in the instantaneous center perspective, the body is in a state of pure rotation about the yes, about the. So now if you have to compute the angular momentum about P, then what's the angular momentum about P? Since it's in a state of pure rotation about P, it's going to be I about P into omega. Right? The angular momentum about P is I about P into omega, even in general rigid body motion. Once you understand these calculations, then the way they like to normally tell you angular momentum is the following. Say if this is the linear momentum vector for a particle P, this is the linear momentum vector which is m into v. This is m into v. For a particle P, this is the linear momentum m into velocity vector v. This is a certain point O. And the position of P as seen by O is position of P as seen by O is then angular momentum about O vectorially. Angular momentum about O vectorially is defined as R cross P. Angular momentum about O is defined as R cross P. R is the position vector of the point with respect to the point O, which is reporting the angular momentum. Angular momentum is R cross P, where the direction of R is this and the direction of P is. So what's the direction of L? R cross P. This is the direction of R. This is the direction of P. So R is like this, P is like this. So take a screw and rotate it from R to P, place it here. It will run into the plane of the board. From R to P, it will go into the plane of the board, yes or no? So the direction of L, that was the sense of L, by the way. That was the sense of L. The direction of L is actually into the plane of the board. Into the plane of the board. R cross P, this is R, this is P. So R cross P is into the plane of the board. That's the direction of L. Right? Now, in order to go from R to P, what is the sense that you are accomplishing? Clockwise. That's why the sense is clockwise. To go from R to P in this case, in order to go from R, which is this direction, P is this direction, you are navigating a clockwise sense. So the sense of L is clockwise. The direction of L is into the plane of the board. Like I told you in one of the earlier sessions, this thumb will give you the direction. The curling of the fingers will give you the sense for your right hand. And if your thumb is normally located, right? If your thumb is located here, it points this way. Some people have two thumbs. One gentleman was a lab assistant in Bella High when I was a student. He had one thumb here and one thumb here. So for him, the right hand rule was not applicable. So it would be sinful to say for all right hands, for normal right hands. If the thumb gives the direction, then the curling of the fingers give you the sense. Or if the curling of the fingers give you the sense, then the thumb will give you the. What about the magnitude? The magnitude of L naught is magnitude of R into magnitude of P into sine theta. Now, if this is D, then this is magnitude of R. D is magnitude of R sine theta. This is mod r, this is magnitude of r sin theta. So mod r sin theta is d and mod p is m into speed. So this is mv, which is mod p into d. mv into the perpendicular distance d. That's the magnitude of the angular. R cross p is the vector description of the angular momentum about a point. P is the linear momentum vector. R is the position of p as seen by Now I'll give you a break, but before that, one more thing, so that you know, I can teach you rotational mechanics after this. So one more thing, I gave you the understanding of torque in a scalar format. In a scalar format, I told you what torque was. If this was a force F, magnitude of the force is F. This was the point O, the force acts at a point P, and this was a point O. Then the torque about O has a magnitude which is F into R. F into R is the torque about. Where this is the moment arm. This is the moment arm, this is the line of action of the force. The sense of the torque? Well, same thing. Imagine this to be a rod hinged at O. If you apply a force, the sense in which the rod rotates will give you the sense of the, right? So we can have clockwise torques, anti-clockwise, right? Now, in vector notation, the torque is understood as follows. If this is a point P where a force F acts, vector force F acts, this is a point O, and the position of P as seen by O is R. The position vector of P as seen by O is R. This angle is theta. Right? Then the torque about O is defined as R cross F. Instead of R cross P, now we have R cross F. Similar structure. For angular momentum about O, we had R cross P. Now for torque about O, we have R cross F. Right? So then, the direction of this torque, well, R is in this direction, F is in this direction. So then R cross F is to the plane of the boat. So the direction of this torque is into. The sense of going from R to F is clockwise. So it's a clockwise torque about O. The direction of the torque is into the plane. Right? The magnitude of the torque is magnitude of R into magnitude of F into sine theta. And like before, mod R sine theta is this perpendicular distance d, the moment arm. Mod R sine theta is d. So this mod R sine theta I write as d. So F into d is the torque about O magnitude. Now, the angular momentum about a given point O is R cross P, like I have discussed, right? The torque about O is R cross F. This is the angular momentum about O, this is the torque about O, right? Now, if I differentiate the angular momentum with respect to time, then I apply the product rule as follows. dr dt cross P plus R cross dp dt plus R cross dp dt. Yes or no? If I differentiate this with respect to time, dr dt cross P plus R cross dp dt. Yes or no? Right? Okay. dr dt is what? Velocity. P is mass into velocity. So direction of dr dt and direction of linear momentum is the same. So if these two are parallel vectors, dr dt is v and this is m into v. So these are parallel vectors, and the cross product of two parallel vectors must be 0. So dr dt cross p is 0. Dr dt cross p is 0. These are parallel vectors, so this will be 0. Now this is r cross dp dt, then p is the linear momentum. Okay, but dp dt is the force. dp dt is the rate of change of linear momentum. From Newton's second law is the external force. So this is r cross f. Okay, but r cross f is torque. So the torque about any point is rate of change of angular momentum about that point. The torque about any point is rate of change of angular momentum about that point. And if the net torque about a point is 0, then L must be constant, isn't it? If the net torque about any point external, this is net external torque, this is net external torque. If net external torque is 0, this would imply that dl dt is 0, implying that L naught must be a constant. Means in the absence of a net external torque about a point, the angular momentum about that point remains preserved. That's conservation of angular momentum. In the absence of net external torque, the total angular momentum about that point remains. That's conservation of angular momentum. I'll give you relief for some time and then start immediately after. Right? Maybe 10 minutes. Go and vent yourself out completely. Right? 10 minutes, we'll start again. Now, hello. If I have a system of particles, in which the particles exert forces on each other, those are internal forces, those are not external forces. Say, in a given system, there is a particle A and a particle B, and they exert forces F and F equal in magnitude but opposite in direction on each other from Newton's third law, right? Then the torque that they produce about any point, these are internal forces. This is one pair of internal forces, right? And now, if you have to find the torque that they produce about a point O, then do you realize that the torque that F produces about O is going to be F into R clockwise, and the torque that this F produces about O is going to be F into R anti-clockwise, right? So this F into R clockwise would get cancelled with this F into R anti-clockwise. So internal forces will never contribute to net torque. The net torque produced by internal forces will always be zero, on any given system. Now, if you have, say, this is a rod which is at rest, a uniform rod of mass m and length L which is at rest. Mass m and length L, which is at rest. This is the center of mass. There is a particle of mass m moving with a velocity u. There is a particle of mass m, particle p of mass m, moving with a velocity u, and it hits a rod at this point, in a manner that after it hits the rod, the particle comes to rest. After hitting the rod, the particle comes to rest. The position where the particle hits the rod is, let's say, at a distance small a from the center of mass. Is at a distance small a from the center of mass. We want to find what happens to the rod. What happens to the rod? How does the rod move? Well, one thing, the particle has come to rest. Now, the linear momentum of the particle now should be borne by the rod. Therefore, the rod develops a velocity of the center of mass so as to preserve the total linear momentum, We started with a linear momentum mu, and then m into VCM is the linear momentum that we produced on the rod because of this small mu. The particle came to rest, conserving linear momentum before collision, mu after collision, capital M into VCM is the linear momentum of the rod after collision. Yes or no? Not only that, the particle, this was the line of action of the particle. The particle had a velocity mu like this. The particle had a velocity mu like this when it hit the rod, right? Now, about the center of mass of the rod, the particle had a linear momentum mu into a. Clockwise or anti-clockwise? Anti-clockwise. Therefore, the total anti-clockwise linear momentum about the center of mass was mu into a. Mu into a was the angular momentum, about the center of mass of the rod, and it was anti-clockwise. Angular momentum. Right? Now, are there any external forces acting on the system? Small m plus capital M is 1 unit. Are there any external forces acting on the system? No external forces acting on the system. No external forces means no external torques. If there is no net external torque, that means the angular momentum is conserved. Now, there is no net external torque about any point. The angular momentum about any point is conserved because there is no net torque about any point. So, I can conserve angular momentum about any point. So, the angular momentum about the center of mass can be conserved, for example. So, what's the angular momentum about the center of mass? So, we will use the center of mass for conservation of angular momentum in this case, right? What's the angular momentum about the center of mass before collision? Mu into a, anti-clockwise, right? Now, because of the impact, the rod develops a velocity, angular velocity omega like this. If the particle hits like this, the rod would develop an angular velocity omega like this. Now, the rod then is in a state of general rigid body motion. What's the angular momentum of the rod about the center of mass? ICM omega. The angle, even in general rigid body motion, the angular momentum about the center of mass will always be ICM omega. Yes or no? Right? What is the angular momentum that the particle has after collision? 0, because its linear momentum becomes 0. The particle comes to rest. So, the total angular momentum about the center of mass before collision is MUA, anti-clockwise, and that must be the angular momentum anti-clockwise of the rod after collision. So, that this then becomes ICM of the rod into omega anti-clockwise. ICM of the rod is known, how much? 112 ml square. So then there are two equations, one the linear momentum equation, the other one the conservation of angular momentum, and then the this will give me the value of omega, this will give me the value of VCM, and I would know know the complete status of the rod after collision, because I would know VCM and omega, right? Say there was a disc like this, a disc of mass m1 and radius r1, and this was the axis of the disc. Say the disc had an angular velocity omega 1, and it was very slowly placed on another disc of mass m2 and radius r2, having an angular velocity omega . Angular velocity omega 2. When this is very slowly placed on top of this, right? After a while, initially they would be slipping between the two. After a while, the slipping will stop and both will have a common angular velocity omega. So after a while, when they flush into each other, these are the two discs, one of radius r1, the other one of radius r2. They would have a common angular velocity omega. Right? Now, are there any external forces acting on the system? So, there are no external torques. So, the angular momentum about the axis must remain conserved. What's the initial angular momentum of the system about the axis? I1 omega 1. I1 is the moment of inertia of this about the axis, plus I2 omega 2, and that must be, now I1 plus I2 is a total moment of inertia about the same axis, right? It's going to be I1 plus I2 into omega. So the omega can be found from conservation of angular momentum in the absence of a net external torque. Got me? Now, say there is a disc. This is a disc and it's in general rigid body motion. Velocity of its center of mass is v1 and angular velocity is omega 1. Now, there is friction on this surface. Right? Surface has friction. Now, because of friction, first of all, realize what would be the net velocity of this point. This is the point of contact. Because of pure translation, it has a velocity v1 to the right. Imagine it to be in a state of pure rotation about the center of mass. That will produce a velocity r omega 1 to the left. So let's say v1 is greater than r omega 1. Then the net velocity of the point of contact would be v1 minus r omega 1. Right? And therefore, the frictional force will act leftwards. Kinetic friction will act leftwards. Yes or no? right? Now, after some time, say the velocity of the center of mass becomes v2 and the angular velocity becomes omega 2. Angular velocity becomes omega 2. Do you realize that at the point of contact on this, what are the forces acting? Mg downwards. There is normal reaction R upwards and there is frictional force. All the forces pass through the point of contact. So what's the net torque about the point of contact? What's the net torque about the point of contact? Zero. Zero. About the point of contact, net torque is zero. See, if a certain point is chosen along the line of action of a force, then the torque about that point must be zero. If this is the direction of frictional force and this is the point of contact, then what's the torque that this produces about the point of contact? R is zero, right? Perpendicular moment arm is zero. So the net torque about the point of contact is zero, which means angular momentum about the point of contact must be constant. Angular momentum about the point of contact must be constant. Now, what's the angular momentum about the point of contact? In this case, there are two aspects, mv1 into r. General rigid body motion angular momentum, mv1 into r clockwise plus ICM omega 1 clockwise. That's the initial angular momentum. Yes or no? That's the initial angular momentum. What's the final angular momentum? mv2 into r about the point of contact. This is the point of contact. mv2 into r plus ICM into omega 2. That's conservation of angular momentum. That's conservation of angular momentum. So, about the point of contact. But can you conserve angular momentum about the center of mass? Why? Because there will be a non-zero torque. Frictional will produce a non-zero torque about the center of mass. So the torque about the center of mass is not zero. So angular momentum about the center of mass is not. Now, in pure rotation, this is the point which is the hinge. This body is in a state of pure rotation with angular velocity omega, with angular velocity omega. The angular momentum about P in pure rotation would be what? In pure rotation, it's going to be I about P into omega. Is I about P into omega. That's angular momentum about P. Now, if I differentiate both sides, then dLp dt is I about P into d omega dt. Hey, but d omega dt is alpha. So, but dl dt is torque. Rate of change of angular momentum is torque. So, torque about P is I about P into angular acceleration alpha. The torque about P is I about P into angular acceleration alpha. Yes or no? So, in pure rotation, about the hinge, you can apply the equation tau equal to I alpha about the hinge. In pure rotation, you can apply the equation tau equal to I alpha about the hinge, where alpha is the angular acceleration. Alpha is the angular acceleration, right? Now, in combined motion, this is combined motion, general rigid body motion. VCM and omega. Combined rigid body motion, VCM and omega. Angular momentum about a certain point O. Let's say this is the center of mass. This distance is smaller, right? What's the angular momentum about O? MVCM into R plus ICM omega. That's the angular momentum about O. That's the angular momentum about O. That means dl naught dt. dl naught dt. Rate of change of angular momentum about O, which is torque about O, net external torque about O, is mr dvcm dt. Right? In general, it could have an acceleration rate of change of vcm with respect to time plus ICM d omega dt. Yes or no? Hey, but d omega dt is alpha. So this in general is mr dvcm dt is acceleration of the center of mass plus ICM into alpha, which means torque about O is not I alpha anymore. Torque about O is not I about O into alpha anymore, right? Yes or no? If O is some point here, if O is some point here, right? But if I take the center of mass, what's L about the center of mass? That means if this O is center of mass, then small r is 0. It will be simply ICM omega. Angular momentum about the center of mass is ICM into omega. Is ICM into omega. So rate of change of angular momentum with respect to time is ICM into d omega dt. But d omega dt is angular acceleration alpha. But ddt of LCM is torque about the center of mass is ICM. Which means again, in general rigid body motion, you can apply tau equal to I alpha about the center of mass, but not about this point. In general rigid body motion, if O is some point which is not the center of mass, you can't apply tau equal to I alpha. Realize that in this case, tau about O is not I about O into alpha, but tau about the center of mass is I about the center of mass into I alpha. So about the center of mass, I can apply tau equal to I alpha in general rigid body motion. Again, in general rigid body motion, that is combined motion, say if I have a point P which is the instantaneous center, this is the instantaneous center, right? This is the instantaneous center. Then this entire motion could be conceived to be pure rotation about P. This is like pure rotation about P, about IC, that is instantaneous center with angular velocity, same as before, right? In a state of pure rotation, the angular momentum is I about P into omega, I about P into omega, yes or no? So, angular momentum about P in pure rotation is I about P into omega, right? Now, I differentiate both sides with respect to time. dLp dt is Ip into d omega dt. Hey, but dLp dt is torque about P. Ip into alpha means torque about point P, which is the instantaneous center, is I about the instantaneous center into angular acceleration alpha. It means tau equal to I alpha could be applied about the instantaneous center. Yes or no? Write down. The equation tau equal to I alpha in general rigid body motion. The equation tau equal to I alpha in general rigid body motion can be applied only about 2 points. Only about 2 points. One, the center of mass. Two, the instantaneous center. You can't apply tau equal to I alpha about any other point except the center of mass and the instantaneous center. If you apply that, you will get a wrong value of alpha. Right? This is a very important fact to remember. Tau equal to I alpha is applicable only about the instantaneous center and the center of mass. Got me? Now, look, if there is a rigid body in pure translation means all particles will have the same velocity as that of the center. And we can replace this entire thing by one particle at the center of mass. The kinetic energy then of this same as kinetic energy of this. So the kinetic energy of this is half m into velocity of center of mass squared. That's pure translation. In pure translation, kinetic energy is half m VCM squared. In pure rotation, so this is a body in pure rotation, and this is the axis of rotation. And let's say omega is the angular velocity of rotation. Look at a particle of mass mi located at a distance ri, right? It will have a velocity vi, which is ri omega. It will have a tangential velocity vi, which is ri omega, because all particles have the same omega. But vi's will be different for different particles because ri's are in general different, right? Now, the kinetic energy of this entire system because of mi is going to be what? Half mi vi squared. That's the kinetic energy. The total kinetic energy would be sum of all of this. In pure rotation. Yes or no? which is half summation mi vi squared, which is ri squared omega squared. But omega squared is independent of I because same omega squared for all i's. So it will come out, and mi ri squared is what? I about AA, I about the axis of rotation. So this is half of I about the axis of rotation into omega squared. So kinetic energy in pure rotation for a rigid body is going to be half of I about the axis of rotation into omega squared. That's the kinetic energy, right? Now in combined motion. So far so good, right? Not an issue. In general motion, there is a VCM and there is a omega. And I want to find, so this is the axis of rotation. Now I want to find the total kinetic energy of this. Like I told you, this could be looked upon as a combination of pure translation plus pure rotation about the because of pure translation, the kinetic energy is going to be half m VCM squared because of pure translation, and because of pure rotation about the center of mass, it's going to be half ICM into omega squared. That's the total kinetic energy in general rigid body motion. Half m VCM squared plus half ICM omega squared, right? Or if you've identified the instantaneous center, if E is the instantaneous center, then anyways you don't have to look at translation. Then it can be imagined to be in a state of pure rotation about the instantaneous center. You can imagine it to be in a state of pure rotation with angular velocity omega, and in pure rotation the kinetic energy is half I about the axis of rotation into omega. So in this case the kinetic energy is half I about P into omega square. Yes, sir. So kinetic energy obtained from here or obtained with this superimposition is the same. Do you know what I'm saying? So that's what we do in as far as kinetic energy calculations are concerned. Now, say there is this symmetrical body in general rigid body motion lying on a surface, horizontal surface, lies on a horizontal surface, and with the velocity of the center of mass being VCM and angular velocity being omega. Velocity of the center of mass being VCM and angular velocity being omega. Write down, a body is said to be in a state of pure rolling, if the velocity of the point of contact, is the same as the velocity of the surface on which rolling occurred. same as the velocity of the surface on which rolling occurs. If the velocity of the point of contact is the same as the velocity of the surface on which rolling occurs, that is, write down, that is, at the point of contact, there is no relative motion. At the point of contact, there is no relative motion between the body and the surface. Also write down, consequently, the frictional force acting on the body, because of the surface, the frictional force acting on the body because of the surface is static in nature, This is what I mean. Hey, suppose the surface is at rest, then the velocity of the point of contact must be zero. Say it's at rest. Say it's a surface at rest. Now, how do you calculate the velocity of the point of contact? Because of pure translation, it is a VCM to the right. Because of pure rotation about the center of mass, it has a tangential velocity which is r omega leftwards. So the velocity of the point of contact is VCM minus r omega rightwards, and that must be the same as the velocity of the surface for pure rolling, right? So this must be zero in this case. So then VCM must be equal to r omega. VCM must be equal to r omega, yes or no? So the velocity of the center of mass must be r omega if rolling occurs on a fixed horizontal surface. Then at any given instant of time, the velocity of the center of mass must be r times omega of the body in general rigid body motion, right? However, if VCM changes, omega must also change, so that at the next instant, the VCM at that instant must be equal to r times omega at that instant, right? It's not like VCM and omega have to remain constant for pure rolling. Both would change, but from instant to instant, VCM must be equal to r omega for the corresponding instant. Now, if VCM changes means there is an acceleration of the center of mass. If VCM changes, there must be an acceleration of the center of mass. So, if I differentiate both sides with respect to time, if I differentiate VCM, what do I get? ACM equals r. If I differentiate omega with respect to time, I get alpha. And where alpha is the angular acceleration of the rigid body, ACM is the acceleration of the center of mass. Got it? So VCM must be r omega and ACM must be r alpha for pure rolling. Right? And if ACM is 0, then alpha must be. That means if VCM is preserved, omega must also be preserved for pure rolling. Right? Which means now, see, this body is in a state of pure rolling. Right? If I have to, this is the topmost point, and if I have to find the velocity of the topmost point in pure rolling, okay, because of pure translation, it has a velocity which is VCM to the right because of pure translation, right? And because of pure rotation about the center of mass, it has a tangential velocity r omega rightwards, yes or no? Yes or no? Because of pure rotation about the center of mass, it has a tangential velocity r omega to the right, right? So, but r omega is VCM, because of pure rolling, so this becomes 2 VCM. Yes or no? Huh? Which means, if you keep a plank here on top, right, and cause this body to roll, that means there is a VCM and there is a omega. Then do you realize, now if there is no slipping between the plank and the roller, then the velocity of the roller must be at the velocity of the topmost point of the roller must be the same as the velocity of the plank. So the velocity of the plank now is 2 VCM, because the velocity of the topmost point is 2 VCM. So the velocity of the plank is 2 VCM, which means if I push the roller so that the body rolls, there is no slipping at the topmost point. Then if the center of mass travels 1 meter, the plank travels 2 meters. The plank travels 2 meters. Got me? If I have to look at the velocity of this point, the leftmost point has a velocity VCM because of pure translation like this, and has a velocity because of pure rotation about the center of mass, has a velocity r omega like this, right? So now it's like this is VCM and this r omega is VCM. So the resultant of these two would be root 2 VCM. The velocity of this leftmost point is going to be root 2 VCM, root VCM squared plus VCM squared. This is going to be root 2 VCM. It's going to be root 2 VCM, velocity of the topmost point. Got me? Of the leftmost point, right? In fact, I could have realized that in a situation where this horizontal surface is at rest, this point of contact has zero velocity. So this could be looked upon as the instantaneous center also. If this horizontal surface is at rest, then the point of contact also is at rest. So the point of contact could be looked upon as the instantaneous center, yes or no? So if the horizontal surface is at rest, then the point of contact being the instantaneous center, because horizontal surface is at rest, well, then in one shot, all other points are in a state of pure rotation about the point of contact in this case. So if I look at the topmost point, at this instant of time, the topmost point is executing circular motion with radius 2r with angular velocity omega. This is 2r omega, so the velocity of the topmost point is 2r omega, isn't it? This is 2r into omega, which is 2 times VCM, right? As far as the leftmost point is concerned, okay, this is r, so this is r root 2. Again, the leftmost point is this, and it's executing circular motion with the POC being the center of the circle. So then its velocity v will be perpendicular to this line, and it would be r root 2 times omega. It will be r root 2 times omega. V must be r root 2 times omega, which is r omega is VCM, so root 2 times VCM, and so on and so forth. Got me? Also realize that the point of contact has no relative motion with the surface. If there is no relative motion of the point of contact with the surface, then the frictional force acting here has to be static. Frictional force will act, but it is static in nature. Kinetic friction would act only in the event there is rubbing, there is relative motion. But since there is no relative motion, the nature of frictional force acting at the point of contact must be static, Are you fine with this? If let's say rolling occurs on a surface which is moving, there is a moving surface and the surface has a velocity Vs. It's a moving surface and the surface has a velocity Vs. And the center of mass has a velocity Vcm and has an angular velocity omega. It's an angular velocity omega, right? Now the velocity of the point of contact would be what? VCM to the right because of pure translation and r omega to the left because of pure rotation, right? So the velocity of the point of contact is VCM minus r omega rightwards, and that must be for pure rolling must be equal to velocity of the. So that's the revised condition for pure rolling. That's the revised condition for pure rolling occurring on a flat horizontal surface, which is itself moving. Right? You understand this basic pure rolling, although stand by.